Suppose we're given two graphs. Y is the square root of x and y equals x minus 2. And if you look at these two graphs, they intersect here at x equals 4. And so starting off at x equals 0 over to x equals 4. And they kind of give you this fish fin look. You know, if you cut off here the x-axis, you get this region here, something like a shark fin, right? So get out of the water if you see one of these. Okay, what we're going to do today is calculate the area of this region. How can we find the area of this region? And as we've already discussed, you find the area of a region by calculating the difference. You calculate the definite integral. You find the definite integral of the function on top minus the function on bottom from whatever the starting value a is to the last value b, from x equals a to b dx, right? That's how you find the area. This is how we find the area. But here we have a challenge. Because although we can go and we can say, well, the function on top is clearly the square root of x. It's clearly the square root of x. When we go to think about what is the function on bottom, well, it kind of depends. If you're here from 2 to 4, the function on bottom is x minus 2. So from 2 to 4, on top you have the square root of x. On bottom you have x minus 2. X minus 2. But if you look at this first portion from 0 to 2, we don't actually have the function on bottom is x minus 2. You know, x minus 2 continues. This line would continue, but we're interested in just cutting off the region up here. So the function on bottom you can think is now like this portion of the x-axis would just be the equation y equals 0, right? That equation there is just y equals 0. So the function on bottom between 0 and 2 is actually just 0. So, okay. I guess this is not a problem. We can do this. The way we find this area is we just break it up into these two regions. One to find the area from 0 to 2, that will give us this region. And then the second one will give us the area from 2 to 4. And we can do this. So this isn't too bad at all. We're just going to add these. So let's solve these, find these areas and solve them. So the area of the first guy is the antiderivative of the square root of x. The square root of x is x to the 1/2. So its antiderivative is x to the 3/2 with a 2/3 out front. You plug in 0 to 2, and you end up with just 2/3 of 2 to the 3/2. Kind of messy, but that's what it comes out to be. And for the second one, we find its antiderivative. Again, the square root of x becomes just 2/3 x to the 3/2. Minus x becomes 1/2 x squared plus 2, because minus minus plus 2 becomes 2x. And then here we're going to plug in 2 and 4. 2 and 4. So let's go ahead and calculate what that gives us. Plugging in the 4. Okay, this might be a little bit tricky, but when you plug in the 4, it's 4 to the 3/2. It's 2/3 4 to the 3/2 problem. We'll come back and simplify that in a second. Minus, if you plug in 4 here, 4 squared is 16. Half of 16 is 8. Plus 2 times x, 2 times 4 is 8. So that's what you get when you plug in 4. Minus, what do you get when you plug in 2? Well, you get 2/3 2 to the 3/2 minus half of 2 squared. 2 squared is 4, so half of that is 2. Minus 2 plus 2 times 2. 2 times 2 is 4. Okay, we could simplify this all, but what we're ultimately going to want to do is add them up. So we want to add up this area with this area. Let's see if we can simplify anything at all. These 8s will cancel. Here I have 2/3 of 2 to the 3/2 minus a 2/3 2 to the 3/2. So those will also cancel. And so I'll be left with 2/3 of 4 to the 3/2 minus, so plus 2 minus 4. And so that plus 2 minus 4 plus 2 minus 4. How about this first piece? What is 4 to the 3/2? What is 4 to the 3/2? Well, you can think of that as 4 to the 1/2 cubed. And that's just going to be 4 to the 1/2 is just the square root of 4, right? That's just the square root of 4 cubed. So that's just 2 cubed. So that's 8. So this guy's 8, so it's 2/3 of 8. This is 2/3 of 8 minus 2. So that's 16/3 minus 2. which is just, 16 thirds minus 6 thirds, that's 10 thirds. So there we go. We found that this area here, this area came out to be 10 over 3. Great. And that's a perfectly good way to solve it. But I want to show you now another way we could have solved this problem. And so for the second approach, what I want to do now is instead of breaking it up into 2 regions, I want to leave this. I want to leave this as just finding the area. I just want to find the area of 1 region. Now, how can we do that? The way we're going to do that is we're going to turn our heads. Instead of thinking about integrating along the x-axis from 0 to 2 and 2 to 4, we're going to integrate along the y-axis. Here on the y-axis, our region begins at y equals 0, and it goes up until you get to this highest point at y equals 2. If you plug 4 into either equation, it gives you 2. The square root of 4 is 2. 4 minus 2 is 2. It's from 0 to 2. You're traveling along this axis. So I want to go from 0 to 2 on the y-axis. And to denote that I'm going along the y-axis, I'm going to put dy here. I'm differentiating along the y-axis. Which means inside, I need to have functions of y. And so what I'm going to do now is I'm going to reimagine these as instead of being functions of x as functions of y. And we do that simply by solving for x. Now I can rewrite y equals the square root of x. That can just become x equals y squared. Just move the square root to the other side by squaring both sides. And y equals x minus 2, that will just become x equals, move the minus 2 over as plus 2, y plus 2. Now, when we integrated along the x-axis, we did the function on top minus the function on bottom. How about now that I'm integrating along the y-axis? Let's say I'm going from some a to b. I'll use capital letters just to note, these are the values along the y-axis. Instead of doing top to bottom, you turn your head and you think moving along the y-axis, the top function is now the function that's to the right. It's y equals x minus 2 or x equals y plus 2. It's the function to the right. And when you turn your head, the function that's on bottom is the function that's on the left. And so now the way we're going to do this, integrate along the y-axis, instead of top minus bottom, the rule is going to be right minus left. Here, the function on the right as a function of y is y plus 2, x equals y plus 2, minus the function on the left is this function right here, x equals y squared, x equals y squared. So this is the right function, this is the left function. Okay, let's just integrate this. And you integrate this just like you would integrate it if there's x's, but you're doing it now with y's. So this is going to become y is going to become 1/2 y squared. 2 just becomes 2y. And y squared just becomes minus 1/3 y cubed. Your power rule. 2 becomes 3, and then it comes down as 1 over 3. And we're going to plug in 0 and 2. And we're going to hope and we're going to pray that we end up with the same area we had before. Let's see what happens. You plug in the 2, you get 1/2 of 2 squared. 2 squared is 4, so half of 4 is 2. Plus, plugging in 2, 2 times y is 2 times 2, that's 4. Minus 2 cubed is 8, so this is 8 over 3, 1/3 of 8. That was plugging in 2. Minus, now let's plug in 0. Well, plugging in 0 is just going to give you zeros everywhere, so that's just minus 0. So you end up with 6 minus 8 thirds. Oh, what's that? 6 is 18 over 3. So it's 18 over 3 minus 8 thirds. And sure enough, it's 10 over 3, just like it was before. So when you have these area problems, sometimes, yes, you could break it up into regions if you want to. But it may be simpler by just turning your head and integrating along the y-axis instead of integrating along the x-axis.